Okay, it's a pleasure to have Bernard Chazelle of Princeton University and now on sabbatical also at the Institute for Advanced Study visiting us for this week. I don't have much time in this introduction to mention Bernard's contribution to computer science. In over 3 decades of work, he has published easily over 120 publications. He is considered one of the founders of computational geometry and is well known for his groundbreaking results on range searching, triangulation, geometric arrangements, minimum spanning tree, fractional cascading, and much, much more. In the past decade, he has been working on sublinear algorithms, and in particular, on property testing and reconstruction, self-improving algorithms, and fast dimensional reduction transformations. And during this time, I had the pleasure of being his graduate student at Princeton. Among other honors, he's a fellow of the American Academy of Arts and Sciences, of the World Innovation Foundation, of the Association for Computing Machinery, a member of the European Academy of Sciences, and much more titles. I just mentioned when Ron Pinter heard that Bernard was about to come to visit, he asked me as the host to prepare the red carpet for his visit. So we don't have a red carpet. It would be fun to have one, but we don't have it. But we are extremely honored to have Bernard talk about his new thing, natural algorithms. And today is talk 1 out of 2, and tomorrow there's another talk, same time and same place. So, please.
Can you hear me? Well, thank you very much, Neil, for these kind, gracious words. I'm extremely honored, very privileged to have been chosen to give this prestigious lecture. I hope I do a good job. I've been very lucky in my life to have had a chance to collaborate with some of the people here in the room, like Professor Ayel Tal, who is somewhere there, I saw her earlier, and Professor Nir Elan, and being friends with many others. And so I do feel a special bond to the Technion for some reason. So I'm going to give two talks, and there's a little change in the schedule, and so this will be the more general audience talk. Since I'm going to talk about the living world, I should be talking about saving your lives and curing cancer and Alzheimer's and so on. But I'm going to talk about something much more important than that, which is why is it that when you put your spoon in your coffee, it gets hot? That's one important question. But the other one is why are tomatoes red? That's another deep scientific question. So that's the topic of my talk. Maybe pause while you reflect on this. Now, the first question, we know the answer. There's a very nice, concise string of symbols called an equation that pretty much tells you all you need to know about it. This is the answer for this one. It's a mess. It's very complicated. Now, the first one is a PDE, a partial differential equation, and the second one is a natural algorithm. It's called natural algorithm because it's an algorithm. It's got loops, conditionals, memory types, the whole thing that makes algorithms what they are. But also they're natural because they're not designed by humans. So you look at this and you say, oh, this is very complicated. Perhaps big data. A big data approach will solve that problem. If we just get enough statistics on this beast, we'll get it to work. Well, maybe not. Beware of linear A. Maybe some of you don't know what linear A is. It's a language in ancient Crete, an island that's not so far from here. And it's a language we know. When I say we, I don't include myself, I include you, but we know everything about it. We know the vocabulary, we know the syntax, we know all the statistics about the language. There's only one thing we don't know. We don't have the foggiest idea what it means. We cannot translate it. We have no idea whatsoever. But we've done all the big data you can do on that, and we know nothing. So what if you're a Martian landing here, and then you see this, and you say, oh, this is a chip. Well, you don't know what a chip is because on Mars they don't have those things. But, well, maybe you say, well, let's see. Maybe I can try to figure out what this thing does. So since you're a Martian, you're very smart, you have access to all these measurement devices, so you're going to plug in electrodes and measure, put voltages, and just see what comes out somewhere. And you're going to use the biggest Martian supercomputers, and they have big supercomputers there, to just crank this out, and you get all these massive data, and you're going to go all these regression formula and classifier, just everything you throw at it. And you will not have a clue of what it does. Can anybody guess what this does? It's RSA, okay? And so my point is that unless you know a little bit of number theory and cryptography, there's no way you can find from these electrodes and these voltages that you're computing RSA. And here's the point. If you don't know that these computes RSA, I will claim you don't know anything about it. I don't care about your voltages. You're missing the whole story. Okay? It's like reading War and Peace and simply counting the number of words and adjectives and saying, yeah, I figured it out. No, you haven't. So this, perhaps, is just like that. You need an algorithmic theory to actually make sense of this. And I want to try to argue why this has to be true. It's not just speculation. This has to be true. It's not always the case, by the way. Sometimes a black box approach just suffices. But I very much doubt that's the case in biology. Now, why is it that they look so different? I mean, a simple PD will tell you what happens to your coffee and to your spoon. Why not a PD for the tomatoes? Why is it so different? Well, the reason that biology is physics plus history. There's a whole history, millions of years of natural selection and evolution, which has imprinted this organism. This is an archaeological record. Whereas this heat equation has always been true, as far as we know. It's always been true. That equation is always held. But we know that the tomato algorithm came after the dinosaurs. Has not been around forever. Okay? So it's something which simply happened at some point in history. And this is of a critical importance. Okay? It is not like physics in that sense. By and large, physics has no history. So you have to treat this not as you would an equation. Okay? When you study the heat equation, its provenance through the history books doesn't matter. You just study what you can study with it. But here, you have to treat this like a historical document. It's very important not to lose that perspective. And now, so math does not do history, and I want to convince you that algorithms do. Now, this is a famous quote by mathematician Israel Gelfand, who said the only thing more unreasonable than the effectiveness of mathematics in physics, it's in ineffectiveness in biology. Now, he was a mathematician who actually dabbled in biology, and so, but perhaps he was settling scores because he was replying to this more famous quote by Wigner about the unreasonable effectiveness of mathematics in natural sciences. And what Wigner was alluding to, he said, it's almost uncanny. Mathematics is very helpful in physics, but helpful is not the word. It seems mathematics is the language of physics. Why is that so? Why is life so easy? Well, if anybody deserves, I think, a prize for explaining why, it probably would be Amy Noether, because she showed, as a mathematician, that the symmetries of the universe. Now, why the universe has symmetries, that we can argue. But given that that the universe has symmetries, the symmetries can be converted automatically, imply automatically conservation laws. And all the laws of physics, essentially, which are dynamic laws, really are inherited from the symmetries of the universe. So this is beautiful. The problem is that history is the great symmetry breaker. Once you put history into physics, all those beautiful symmetries are gone. And in many ways, so is mathematics. Okay? Or so is classical mathematics. Now, why these changes? Absolutely everything. Physics has universal laws. Universal because if they apply here, they apply everywhere, and they apply over time also. Biology has only one law. As far as we know, it's adaptation and there's formulation. So in many ways, you might think it's more, well, of course, it is physics, so it's got all the laws of physics also. But on top of that, it's got adaptation. But, and this is my point, it's also got things like types, memory, conditionals, and this whole thing forms, I call natural algorithms, and has to be investigated as a whole with all these components at once, and certainly not just this one, which also on its own has got to be the weakest law, the weakest universal law you can imagine, weak in the expressive sense of the word. The second point I want to make is that not only natural algorithms are the way to model the living world, but it's also the way to study it. Now, maybe this is obvious, because you know that to study mathematics, you need more mathematics. Mathematics is a closed system. And what's not closed are the problems. You get the problems from physics or biology, but once you're in mathematics, that's a closed world. And in many ways, that's true of algorithms, that some algorithms can be handled by classical mathematics. There are very few of them. I mean, you can count them on one hand. Most others, natural or non-natural, you have to use algorithms to study algorithms. So algorithms will play two roles. One is that of a modeling tool, the other of an analytical tool. So I do make these two distinct claims that natural algorithms are both the language and the toolkit of the living world. Now let's look at types. Types as in, type theory and that sort of thing. Types responds to the limitations of set theory. Once you say that a set has elements and maybe the set is itself a subset of another set, well, this is very useful in mathematics. But in biology or in computer science in general, this quickly runs into limitations. For example, this is Messi, greatest soccer player alive, and this is a soccer ball. So to some extent, we're making similar statements here. This is a soccer ball, means that it's a set of molecules, it's a set of elements. And there are the tools of physics and chemistry and so on can help you figure out what's in there, why this bounces when you kick it and that sort of thing. Now, this is the world of physics. We have sets and elements and some dynamics on top. But this is Messi. That's not a set. It's not a set for many reasons. I'm not talking about the philosophical aspect of a human being. No, just it could be a tulip. That'd be the same thing. I mean, a living organism is not a set because, as you know, most of these cells will be entirely replaced within, 7 to 10 years. So what is Messi anyway? Maybe his neurons are there, but everything changes constantly. And yet, there is such thing as an identity. I mean, Messi remains who he is. There's no doubt about that. But what is it? It's clearly not a set. So you have to go into types to begin to explain what it is, because you have to bring in function before, at the outset, whereas in set theory, functions come next, come after. Second is the notion of abstraction, that you look at this thing, and you've got to ask yourself, but are we... See, this is an abstraction, because that's not a tomato. And actually, that explains only why tomatoes become red. First they're green, and then they become red. Why do they become red? Why not purple or something? And so this explains this, but it tries to explain... I mean, there are many problems with it. For one thing, we don't even know whether it's correct. And the other is... Now, these are variables that have been put into that diagram because we've made measurements and we followed locally causal chains, but how do we know they really matter? I mean, are these really the right variables that we have? And this is an important question all physicists ask because the universe is too big. You cannot make statements about every single particle. So you do have to talk about collective variables that sort of summarize what's going on, and you have to do it the right way. If you do it the wrong way, you end up with things like vital forces, phlogistones. These were notions that have been abandoned but were prevalent in physics 200 years ago. So you've got to know what you're doing. One of the triumphs of thermodynamics was that when you try to understand a steam engine, you see, it makes perfect sense from a reductionist point of view to understand this thing, just to measure all these parts. So you just measure all these parts and you try to have equations relating all of this and try to make sense of it. And you'll get nowhere, all right? Because, well, there are all kinds of problems having to do with relevance, pertinence of variables, and the dynamics, the chaotic effect, and so on. So now we take it for granted that there are just a handful, maybe 5 or 6 variables, parameters, that pretty much describe everything you need to know to make statements, the statements that matter about a steam engine, and the others just don't matter. And, you know, this is trivial to us because we taught this in high school or in college. But in fact, these are true scientific breakthroughs. This is where true genius appears, when something extremely complex gets reduced down to virtually nothing, and yet you capture the essence. How do we know that this captures the essence? This is very important, to do the right abstraction. It's not at all obvious, and our intuition is most likely completely wrong. Okay, so if you look at the standard language of evolution, like fitness, phenotypes, these concepts are, how do we know these are the right variables? First of all, they're usually not well defined, but these are real problems. Now, another one is scale separation. So in 1905, Einstein, one of his, amazing, one of many of his amazing breakthroughs was everybody was working on strange open questions in acoustics, phonetics, all of that. And Einstein just said, what are the really big open problems in physics? But big in a conceptual sense, not practical or anything. So there are several that you, of course, know about. But Brownian motion was one of them, because nobody could explain why Brownian motion occurs when you put a little particle from a grain of pollen into water. It just starts moving around. At the time, people didn't believe in the concept of atoms, so there's a bit of a problem. But in fact, it's because of Einstein that people actually began to believe that actually what happens is this thing sort of bounce around like crazy, and you have this random walk, but you cannot look at it. It's too small, okay? So if you believed in Newton, as you should have, then you say, well, after all, these are just Newtonian forces. So you just write down the forces of Newton, and you have a deterministic mechanism, and then you just figure it out. It's all in there. It's deterministic, by the way. And in theory, that's true. But instrumentally, this gets you nowhere because it's just too big. It's intractable. You cannot do anything with this. That's the problem. So then you say, okay, maybe we can have a more tractable thing. So this is where Einstein steps in. Say, well, maybe we can just pretend that it's stochastic. It's like a random walk. These little particles are pushing this big guy around in kind of random fashions. The angles are kind of random, and so this thing is just going to move around like some sort of random walk. So this becomes stochastic. Stochasticity is only in your head, by the way. It's certainly not a stochastic process. For example, it's reversible, which shows it's not stochastic. But that's the way you're going to reason about it. That's the right abstraction. And this is very important to notice that Einstein would have failed if random walk was not a scale-free process. He could not have done this. Because again, when you observe it with a macroscope, especially in 1905, you couldn't see that. You could see only a very coarse. It's like if you looked at it from very far away. Okay? So you still saw this thing bouncing around, but you saw it at a totally different scale. I mean, it's still mesoscopic scale, but it's a different scale. And the only reason why it works is because in that range, it's scale-free, which means it doesn't matter at what scale you look at it. Any scale is good enough because you don't change processes as you move scales. This was a key to make this happen. Now, if you go even further away from it, then what you can say is that, well, forget the rest. Look at the probability of this yellow thing being at a certain spot at a certain time, and you can write a deterministic PDE, the diffusion equation, that will tell you the macroscopic nature of this beast. I know this is all standard physics, but to me these points are absolutely crucial if one wants to understand how algorithms might work in the context of biology. Okay. That there's a whole sequence of small miracles that happen for making this thing that seems kind of that you have these different scales, and they operate very they all reason about the same process. We're looking at the same thing. It's the same elephant we're looking at. But we're looking at it from different angles. And in particular, we go from deterministic to random to deterministic. Okay, this just depends on how convenient it is. And this is the right abstraction that you have in physics. Now, in statistical mechanics or other things of physics, of course, this concept of abstraction is absolutely essential. Again, because there's too many particles. And so you see the same scheme happen again and again. But there's one thing that is specific to physics that you don't find as much or at all in biology, which is there's this arrow. Scales are nicely separated, and one sort of, supervenes upon the other in a natural way, that one summarizes the other, which summarizes the other. So there's an arrow that corresponds to the scaling, and then you go nicely from one description to the next. These are very common in physics. But in biology, the problem is that this is back. And all the scales, spatial and temporal, I don't have temporal scale here, but get all mixed up together. So the whole idea that you get in renormalization in statistical physics gets all banged up because everything gets all tied together. And now I could give you many examples of that in biology, but my favorite is this one. It was a cartoon, a recent cartoon in the New Yorker. I don't know if you can see this, but so you've got this medium-sized fish surrounded by tiny fish. So the medium-sized fish is okay, because tiny fish is not going to eat it. Until the tiny fish decide to get together and form a big fish. And that's what they do. They have a nice school of fish that it becomes a big fish. Now this big fish will eat this one, or at least this guy will think he's going to be eaten. So its behavior will be changed completely by the emergence of a big fish. The fact that big fish is completely fictitious is irrelevant. You can imagine it being real. The point being, you see how the arrow goes up and down. It goes up because you go from small fish, which emerges into a collective, which is this big fish. So the arrow goes up in the scale direction. But now it comes back down because up on that scale arrow, there's a new thing that appears that now has an impact directly on this. Okay? And this phenomenon really changes everything. And so here's my point. My point is that while equations, when all the scales are separated and there's a nice arrow that takes you from one to the other, then you still have the Noether symmetry type things. You can still hope to use traditional mathematics. And renormalization really uses, which are perturbative methods in physics, still use standard mathematics. But here, when this sort of influence between scales is all mixed up, then you're really out of, you don't know what to use. In particular, you don't even know how to talk about it. And so the problem is not so much we don't have the right equations. I would argue we don't have the right language. Okay? And certainly the language of PDEs is inadequate to even express, let alone to solve or answer the questions. But even to express them is inadequate. That's my point. So to test these wonderful ideas, I had to come down to earth and say, well, let's just manufacture a toy model, which I hope is expressive enough to test these ideas. So I think sometimes people think I do what I'm not doing. They think I have these models to try to explain how fish swim and how birds fly, but that's not what I'm trying to do at all. These are much too ambitious goals. I'm just basically trying to figure out what's the right language. So let's test some of these ideas where scales come together, and can we, out of this mess, get some threads, some ideas that we can put together and form a toolkit, which then we can use for birds and things like this. I still use birds and fish because they look nice, and then they're nice to draw. And you know, you read this, you see a little fish. Even if the rest is boring, at least you see a fish. That's nice. And maybe I should put like little pop-ups with like sushi or something. Then people can actually eat the fish. Maybe they will like it even more. So the intuition behind the model, which I will describe now, is this. You have particles. Imagine particles like in physics, and they will move around, and they will interact in all kinds of ways. But each one will have its own physical law, okay? So this is the fundamental difference, which is now, so we call them agents, because maybe particle is not the right word. You no longer have universal laws of physics. Everybody decides what physical universe they live in and which laws apply, but they live in the same bowl and see what happens, okay? That's what I'm trying to do. Okay, so there's these so-called applications, but they're not applications, they're excuses or alibis or whatever you want to. Yeah, so let me describe the model. And so I guess on Tuesday, which is tomorrow, I guess I'll be talking about more specifically about the technical aspects of this. But here I'll just give you a bird eye iceberg view of this thing. Okay, so you have points, agents in d dimensions. D is a parameter, but think of high dimensions. This dimension does not have to be very big, but think of it maybe a few thousand or something. That's, so these are humans, but they don't have to be humans. They can be anything, okay? It's, but just to give you an example, so, I mean, it's not necessarily their position like in the plane. It could be that you're in some phase space, say in 2 dimensions, where you would have people according to the political views. So we say left wing, right wing, evolutionist, creationist, and well, of course, in America, there's a big. These are heavily correlated data, and you can guess in which way. But presumably, they will interact together, and they will improve their view of the world, or maybe do the opposite. But things will change. But anyway, this is just to say what these agents, what the state might be. Okay, could be things in their heads. Could also measure their blood pressure while they argue. This could be a useful thing to know. Anyway, so the point is they will communicate with a graph, but the graph will change. The graph will respond to the evolution of the system. All right? This is critical. So at any given time, if you take a snapshot, things will look like this. And the meaning is that she listens to her. That's the meaning of this arrow. She, on the other hand, does not listen to her because there's no arrow going the other way. So the meaning of an arrow is that you listen to somebody. All right? So you're influenced by that person. All right? And we'll explain how this works. So the question is, what about this guy? He's listening to 3 people. Why? Why these 3? So here's the thing. He's going to have his own decision procedure. He has an own algorithm that will decide who he listens to at any time. But the algorithm does not depend on time. It simply depends on the position of all the players. So at any given time, there's certain placement of all these agents. And depending on that, so this guy has access to the position of everybody. And depending on that, he'll decide, oh, I will listen to Freddie, I'll listen to this, I'll listen to that. Okay? All right. So this can change. It's also important to know that all these algorithms can be different. Everybody can have their own way of selecting who are the neighbors when. They don't have to have the same. Okay? They can all be different. That's one sort of algorithm. Is the graph, the communication algorithm that tells people who they talk to and who they listen to, who they listen to. Now there's another one which is about the dynamics. What do they do? So each agent has its own action algorithm. An action algorithm, now, so it's a different algorithm, and what it does, let's take her example here. So she has her own algorithm, and now she will simply look at her neighbors, which is herself, this guy, and this woman. And she will simply look at these three and will use her algorithm, which is a function, of these three people, all the information they have of their states. And out of that will be produced an action. And an action is simply a motion. She will move somewhere, like she moves here, for example. Okay, you move in that space. Okay? And again, everybody can have their own different algorithm. Okay? Is it clear? Now, notice she moved inside the convex hull. She doesn't have to. But the class of systems where people move within the convex hull of the neighbors is very important. And well, I'll mostly be talking about this. And these are called diffusive systems. And they cover all diffusion, all cases of generalized diffusion, everything. You can simulate with this, but you can do much more. So diffusion is particularly important and we'll treat it separately. Okay? So that's the model. Pretty much that's all you need to know. Well, you need to know a little bit more. So this is a little animation. So time 0, they're here. Everybody has selected their neighbors. The action algorithm tells them to move, so they move. Then they get another set of neighbors by applying their algorithm again. And the action algorithm again, they move. And this goes on forever. And the question is, can you make any statements about this? This is a very general model. Still, can we make any statement? I mean, what's going to happen? Does it go on forever? What happens? So, now, philosophically, here's what we want to say. The action here, for the diffusive case, is to stay in your convex hull. You have to stay in the convex hull of your neighbors. Now, that's an assumption. You might want to change it. When we talk about bird flocking, that assumption will change. But it's important to have, to restrict. Philosophically, the action has to be limited because these agents have to be, this whole philosophy of emergence is that these agents have to be cognitively limited. If this guy is a Turing machine, he doesn't need anybody else for life. Okay, so the point is agents are limited cognitively and they're going to get help from their friends. That's the whole point we're trying to understand. So it doesn't make any sense to have a very general action thing. So we don't mind restricting the action. On the contrary, the edge selection can be very general. Okay? Like for example, typical case for bird flocking is that every bird joins to the 6 nearest neighbors. Okay, fine, that's a possibility. But I want to make it much more general. For example, you could have your edge selection could be, I will only join to my neighbors in a traveling salesman tour, for example. It's hard to compute, but that's if you 2 neighbors. Okay, fine, so you can do that also. But I want to be even more general, because I want this to be very, very general, okay, to cover any case that might come in. So I will throw in the entire first-order theory of the reals, which is pretty much the last theory that's decidable in that world. So, for example, well, no, I won't give you some examples. I'll give you more examples, but tomorrow. So here's the point. Edge selection can be very general. Action has to be more limited. That's part of the philosophy. So these so-called diffusive influence systems form a very rich theory. Okay, so if this is the set of all systems, this is the set of all such systems. So a system is a point in that space. All Markov chains occupy just a tiny little speck of dust in that universe. Okay, so this theory will completely include all of Markov chain theory. It's easy to see why that's true. By playing around with this, you can design a Turing machine. Okay, so it's very powerful. Even though each agent is extremely limited, each agent can only move to the convex hull. As soon as you put more than like 15 of them, then you can get a Turing machine. So you can get chaos, all regimes of chaos, limit cycles, fixed point attractors. You can get all of that. You can find examples of all of that. So now, but you don't know where the separation is. So that's what I want to find. Experimentally, if you play with this by simulating, pick your favorite algorithms for selection and favorite algorithms for action, even random ones, just generate them randomly and see what happens. It always goes like this. It always ends up to look periodic. Now, it's not exactly periodic. You can check. It's asymptotically periodic, so it gets closer and closer to a limit cycle. But it always happens. So you have a limit cycle. In fact, you have lots of limit cycles. If you take the starting position and you shift and you perturb it a little bit, you get another limit cycle, which is different. So you have all these attractors, and you can count. There's an okay. So no, I'll talk about this tomorrow. But there's at least an exponential number of attractors, of attracting sets like this. Okay, and by perturbing the system, you can go from one to the other. Now, what I showed recently is that this class is actually trivial as measure 0. So yeah, they are Turing machines. Yes, there is chaos, but it's pretty hard to actually, if you perturb the system a tiny bit, they go away. Okay? So actually, in reality, if you admit perturbation of these first-order sentences, like when I say your nearest neighbor, if there's a tie by epsilon, I don't care which of the two I take. That's what I mean by. Then basically, you only have attractors, or limit cycles, or things like this. That's the only thing. And now, this is surprising for several reasons. First of all, it's actually, well, first of all, it's very depressing because these models grow out of whole literature in sociology on how people polarize, how political systems are polarized. There's something called social epistemology. How do people agree on certain scientific truths, for example? And how does that system of information and belief propagates? But what this shows is actually it doesn't matter how often we talk to each other in search of enlightenment. We'll eventually just caught in a cycle. Just repeat our opinion in the same order, which is even worse, to add insult to injury. The only hope is the period will be so long, we don't realize that. If the period exceeds the number of seconds in your life, you're okay. Because you'll be dead before you have a chance to realize that you actually are heading back to where you started from. Okay, so maybe that's a nice way to think some of the benefits of a short life. But there's also a very interesting, I think, phenomenon of criticality. Let me explain what I mean by this a little bit. So here's the deal. This bubble here represents all the systems possible. So by system, I mean not the starting position, the set of algorithms. You give me a set of action algorithms, a set of edge selection algorithms. That gives me a system. Okay, that's 1 point. That's 1 point here. Now, you can define perturbation in a natural way. You can define one-dimensional perturbation. Okay, 1 degree of freedom by just perturbing the coefficients just a little bit in one direction or another. So pick your favorite small epsilon 0 being 1/100 or something. And if you zoom in here and you look closely what happens, this is very interesting. Most likely, the system is a limit cycle everywhere, is asymptotically periodic everywhere, most likely. But there will be cases where you do have Turing machines and chaos and everything. You have to, because I showed that earlier, that this thing exists. It has to be there somewhere. The geometry is very strange. It is contained in all the chaotic region is a measure 0, but it's less than measure 0. It's a Cantor set, okay? So it has fractional dimension less than 1, and so it sits on this very, very bizarre fractal-like shape on this line. These are all the difficult, all the hard cases, and these are critical. These are the critical perturbations. You know, in statistical mechanics, it might be used with the Ising model that there's one critical temperature, if at all, but there's just one. But here, there's a whole infinite set of critical values and they form a fractal set. This is kind of neat. So. Okay. Now, if you want to push the comparison with Ising model, so I hope at least some of you are somewhat familiar with this. So these are these I've been very fruitful, source of lots of breakthroughs in physics to explain things like phase transitions, with water or things, or magnets, magnetization, and things like this. And the big story is that you have processes that physically are totally different. One is a gas, water, other is made of magnets and stuff, and yet they have universal behaviors. I mean, they seem to be following the same laws. Now, this is really, really strange. So in the Ising model, what happens, you have these little particles. They don't move. I mean, the particles jiggle, but they don't move in space. They're stuck on the lattice. But there's an excitement coming from the outside, source of energy from the outside, so they keep jiggling, okay? So you can maintain the amount of excitement that they have. Just like here, the agents keep interacting forever, okay? This is this form of energy that goes into the system. In the Ising model, the particles want to jiggle in sync in the so-called ferromagnetic model. The particles want to be like their neighbors. It's like kids who want to be like their neighbors. If you jiggle up, I jiggle up. And so I want to do that. And similarly here, because of this diffusive process, diffusion means that the agents want to move toward the neighbors. They want to be like their neighbors, which is also very similar, okay? And in both cases, you have criticality. Now there are some differences. Usually, you get lots of metastable states, only like in things like spin glass, whereas here you get lots of limit cycles all the time. Okay, so you have to enrich the model a little bit to pursue this comparison. But there are differences, though. Here, the topology is fixed. There's a natural notion of scale here. You can talk about small range correlations, long range correlations. This is all very meaningful. Here, it's not even clear what it means. The topology changes all the time. Your neighbor today might be extremely far away tomorrow. So those things change all the time. There's no natural scaling. So that's a very big difference. The number of critical points is infinite here. Usually it's a single. Those systems, usually when you look at them, are equilibrated or they're close to equilibrium. Here, that's the whole point. They're completely out of equilibrium. And that's what algorithms do. If they're not out of equilibrium, they're boring. And finally, these are stochastic systems and these are deterministic. But now, this might be shocking for a physicist, but for computer scientists, this is straightforward. I mean, you know, for us theoretical computer scientists, probabilistic is just another form of determinism. I mean, you just have pseudo-random number generators. These are essentially deterministic objects, but they behave totally probabilistically. Well, that's what we mean by this. And so it's a purely phenomenological interpretation of stochasticity, which I think you find also here. Now, and this is the point, influence systems have no eigenmodes. Now, maybe that doesn't mean anything to some of you, but in the whole thing of dynamics and control theory, you're looking for modes. What are modes? When you have a complex system that sort of moves, that has a dynamic, the modes is what allow dimension reduction. It is to say that the overall dynamics is a composition of certain one-dimensional or low-dimensional patterns, dynamic patterns that you can understand. Now here, there's no such thing because all the scales, as I was saying, keep interacting, okay? So you need algorithmic proofs. You need a different way of attacking these, the Lyapunov exponents and Lagrange work because there's no such thing. I mean, in particular, and this can be sometimes shocking for people doing dynamics, all the Lyapunov exponents are non-positive. Now, usually, when you have chaos, usually there's a positive Lyapunov exponent somewhere. But not here. They're all non-positive. And yet, you're going to have not just chaos, but a Turing machine. The role of scaling, now I'll explain this in more detail tomorrow, but as these move around, you can look at periods during which, let's say this group of 3 people is as a one-way isolation. Suppose that there's no edge going from here to there for a certain period of time, which means that these 3 people don't listen to the outside world for a certain period of time. You don't know for how long, but for a certain period of time. Let's say that happens. It means that you could solve the system separately because the outside has no influence on this. So this is very useful. But what about the other? Well, those guys listen to this. They listen in. They cannot interact, though. So there's no feedback loop between this and that. It's a one-way influence. But that means that you can do coarse graining the way you do in renormalization theory. And you can replace this complex system of 3 agents by one super agent, which is more complex than a single agent, but much simpler than a whole complex thing. So the super agent now now what you have are two systems which are almost decoupled. They're not totally decoupled because this goose is really a coarse-grained summary of this. But this is how you can do coarse graining, and you can do it only for a certain time period, which you don't know ahead of time, because you don't know how long this group will not listen to the outside world. At some point, you might decide to listen to the outside world. There's no telling. Okay, so in that sense, you need to use graph algorithms and combinatorial thinking and so on. You cannot slap a differential equation and simply crank it out. Okay, I hope this is very clear. Now, another thing is about the role of memory, which is extremely important because in physics, memory does not play a very big role. Yeah, I know it does. Sometimes they're delayed and so on. Integration is a way of doing memory. And in statistical mechanics, of course, you have things like Hopfield networks, which is a way of doing memory. But here, it is so much more essential that memory is what gets all the time scales mixed together. And here's an illustration of something that can happen. Okay? Now, remember, the main result is that most of the systems get trapped into a periodic orbit. I mean, they get increasingly close to a periodic orbit. That's what's going to happen. Once you are in orbit, you've lost all memory of where you came from. You have complete amnesia. That's what it is to be stuck in a cycle, in a limit cycle. You lose all information about the beginning. But here's what can happen. And you have to, by the way. As long as you have memory, you cannot be in a limit cycle. All right? Now, here's what can happen. That this goose, at the very beginning, listens to her and acquires a lot of her information at the very beginning. And then, for the longest time, this goose is not going to do anything. And the rest will evolve and into a limit cycle. Now, after a while, you wait until this converges. It converges into a limit cycle, like this. She has become amnesic. She has lost her entire memory where she came from. She has to. But now, here's what could happen. She decides, because after all, she has her own algorithm, she decides, with the help of others, that after all, she'd like to listen to him one more time. This is a disaster for the system, or it's maybe very good, depending on your point of view. She recovers her memory. Well, maybe that's a great thing. I mean, we should be very happy about this. She's recovered her memory because she's talking to the goose, and the goose had memorized her at the very beginning. Now, she had lost her entire memory, became amnesic, but somehow she snapped out of it, talked to him, and recovered her memory. Now she has her own memory. She cannot be in a limit cycle. But the theorem says she's going to have to be in the limit cycle. So eventually she will. But the point is that this delayed the limit cycle because when she talked to the goose, it totally killed off the entire converging process of the past. The whole time has been wiped out. Let's say that you get charged shekels waiting for the limit cycle to happen. This is a nightmare. You're going to have to pay much more money. Okay? So the goose plays the role of DNA. Okay? The goose plays the role of long-term memory, where you deposit something, the rest goes into wild motion and so on. And then something happens, you go back, recover the memory, and the whole dynamics change completely. Okay? This is the kind of game that you have to think. And you see how some ways combinatorial that thing is? Okay, so I'll say more about influence systems, and I just don't have much time left. And so, yeah, so you play with one example of, this is a particular influence system that has been studied a lot, which are, you look like you're you have a fixed disk of a fixed radius, and you take the average, you move to the mass center of the averages here. And so you get this kind of motion, you repeat forever. And this is a picture of 10,000 of them. And you see, it's interesting. When you start at random, it's kind of isotropic, but then it becomes one-dimensional. Eventually, it becomes zero-dimensional. So you break all these symmetries. And we showed recently with a bunch of co-authors, including Mark Breverman, who was here many years ago, maybe too many years ago for people here to remember. He was an undergraduate student, and we showed these processes polynomial. Now, I'll conclude by going back in time. Actually, I started working on this by looking at birds. And I still love bird flocking and try to understand things like this. And so I looked at the Cocker and Smale are mathematicians. Vishek is a physicist. It's become a very famous model where every bird looks at their neighbors and update their velocity. So they don't update their position, they update their velocity. The velocity changes by taking averages of their neighbors. So you have a natural graph structure, the way we did. There's a non-directed, and it just changes. Just update. So velocity is here, you take the average with your neighbors, and so on. And the question is to know how quickly, or if at all the velocities will be parallel, so the birds will fly in a flock. And so, this changes, and so I showed it actually always converges, which was not known without assumptions. So, because usually people make assumptions, but assumptions like the graph will be infinitely connected. But this is really giving away the game, because in many ways that's the whole point, to know whether it will be so. So there's a period of fragmentation, and then the birds finally reach a situation where the flocks can only merge, but can no longer fragment, and then you reach steady state. Okay? Let me skip this because I'm running out of time. And just something kind of interesting, which is one of the main tools to prove these things is to use algorithms, okay, not equations. And so what do I mean by this? Suppose that there's a baton, like when you run in the Olympics. You have a baton, and there's only one, and a bird holds it. And the bird can hold on to it as long as it wants, or it can pass it on to its neighbors. That's it. So with this, you can design protocols for birds. For example, I'll keep the baton for 2 steps. Then I'll give it to the guy right ahead of me. That's a protocol. Okay, question. Can you design a protocol? Does there exist a protocol such that the baton moves almost in a straight line? So one has to define. If you have a random protocol, the baton is going to move in zigzag all over the place. But is there a protocol that keeps the baton almost... Imagine the baton is made of dynamite, and if it takes a turn that's too sharp, it explodes. The birds are not happy about that. So they really have incentive to keep the baton straight. Now, if you can answer this question, which is really an algorithmic question, then you start building infrastructure that is absolutely essential to understand these dynamics. Again, these are really algorithms used for the benefit of algorithms. Okay, I think I'm out of time, or maybe I can continue with questions, but I didn't want to.
Well, let's thank the speaker. Questions?
No.
Your pictures are on 2D. Is anything dependent? I mean,
For the birds or for the...
For the circles? And
No, this is in any dimension.
center of mass?
Yes.
Is it reduced to a...
You can do this in any dimension. And also the center of mass could be weighted. You could actually put weights and the same result holds. Yeah.
So it doesn't depend on dimensionality?
No. I mean, yes, the convergence time depends on it, but it's polynomial in the dimensionality. It's all polynomial. But it does not depend in a fundamental way. Freddie?
How do you actually use an algorithm to prove something about another algorithm? Because you need a proof.
Yes.
You know, like a proof is not an algorithm. A proof is a mathematical statement that the algorithm is going to end, that some variable is going to get a certain value or something like this.
Yes.
So how do you actually go about?
Okay, so
You'll give an example next.
yes, yes. So I can try to answer this in 2 ways. Here's an example, in fact, which I used for this. Think of, for example, the wonderful theorem of linear algebra. The rank of a matrix can be defined either with respect to the columns or the rows, and it's the same number. Now, there is a structural proof, which is not at all algorithmic. It's just a very simple proof that just shows why this has to be true. Fine. But there's also Gaussian elimination. I mean, if you do Gaussian elimination, you will see that the rank is the same. That would be an algorithmic proof, because Gaussian elimination is an algorithm. Now, the reason I mention this is important, because, and I really think this is an important metaphor, because actually I've used it, not for the baton passing, but for some other algorithm that I used, which is the following. So you're going to have products of matrices, and you want to diagonalize them. Except it's totally useless to do that, because these matrices don't commute, and they have no common eigenbasis of any sort. So in fact, the spectrum is entirely useless. Okay, that's really too bad. It's really too bad. So you could look at a proof that a matrix can be diagonalized, or when it can. Sometimes it cannot. Let's say a matrix with different eigenvalues can always be diagonalized. Okay, fine. You can look at the proof of that. And now you can try to apply this proof on these products and see that the proof every time requires different bases. The projections are in different spaces. So that's totally useless. So the proof is useless because the theorem that you're looking for is false. But now here's what you can do. You can look at the proof that doesn't work, but you can think of it algorithmically, and you can change it. Forget the theorem. You're not trying to prove a theorem anymore, well, you will, but no longer at this point. Here's what I'm trying to say. Take a theorem that is true for an object A, and try to apply it to an object A prime. And you realize that the conditions are not met, and therefore the theorem is false for A prime. Even though A prime looks almost like A, but it's false. What can you do? Here's what you can do. Take the proof and look at the spot where it fails. And imagine the proof is kind of algorithmic. And by the way, most proofs are algorithmic. And you see where it fails. And now you simply build different objects. You change the algorithm, not to reach the conclusion that the theorem applies to A prime, because you know the answer is no, that's not going to change, but simply to obtain something else. And so I don't have time to give you specific examples where I use just that technique to basically force a spectral frame of mind, if you will, on structures where basically there's no spectrum, there's no modes. So in that sense, you see, if you don't care about actually proving a true theorem, you have much more freedom. You can take the proof and just change it. What if you never stop because you say, oh no, but this is not true, I cannot do that. But in physics, they do it all the time. They take fractional dimension, right? Like they do renormalization in dimension 4 minus epsilon. Well, what the hell is that? But yet, and then they take an integer that tends to 0. An integer that tends to 0. You try that. And, but in some sense, they're doing exactly the right thing, because maybe I said the wrong thing.
You are under attack.
Okay, well, these are nice last words. So.